Hello everyone. Previously we had discussed on the topic segment tree, right? So today we'll be discussing on the topic Fenwick tree, right? So let's get into the definition part here. What does the definition part say here? A Fenwick tree is a data structure that efficiently supports prefix sums, right? So that efficiently supports prefix sums and updates on big of logarithmic n, right? A Fenwick tree is a data structure that efficiently supports prefix sums and updates on the big of logarithmic n time. So mainly when I say big of logarithmic n, this will be mainly used for the optimization purpose. So right, when the constraints are very tight, if we are solving the competitive coding or if we are giving lead code contests or anything, right, when the constraints are very tight and suppose we have to go with the prefix sum or the updates, right, then in that case we can make use of the Fenwick tree, right? So it uses bitwise operations. What it does, it uses bitwise operations to store cumulate sums in a compact array, right? It uses bitwise operations to store the cumulative sums in a compact way, right? So each index stores the sum of specific range of elements. What it does, each index stores the sum of specific range of elements. This part is very important. Just remember this one. Each index stores the sum of a specific range of elements, right? So this is also very important. Fenwick is a data structure that efficiently supports prefix sums and updates on big of log n. Whenever there is updation required, usually we go off the Fenwick tree. Usually we go with the Fenwick tree, right? So you can just make use of this template. Actually, you can just make use of this template whenever the problem is given on the Fenwick tree or the segment tree. You can just go with this, and accordingly with certain this one criteria or certain this thing conditions that they have given in the question, you can just modify the this one method a little bit. You can just tweak, right? So you can just tweak or you can just modify based on the criteria or the condition that they have given in the question, right? You can just go with the this one class segmentary, this whole segmentary class. We can just save this one, and we can just make use of it, on whether it may be in the lead code or whether it may be in any competitive coding platform, right? It doesn't matter. So same goes with the Fenwick tree as well. And you can just I'll just explain this one with a very simple example. Basically, we can just make use of the template within the lead code or this one competitive coding platforms, anything, right? So I'll just go with any platform I meant. So let's go with a very simple example. So first I'll just go with a Fenwick tree for prefix sum. So I'll just go with class. So this one, Fenwick tree. And one more thing, Fenwick trees are also known as BIT or the binary index trees, right? So just keep this in mind. Whenever you hear the word BIT or the binary index trees, it is nothing but the Fenwick tree. It is called with different names. That's it, right? So I'll just go with a class Fenwick tree here. So let's go with the initialization part first. So let me go with init. So let me remove this one. Along with the self, I need n as well here, right? So next step is I'll just initialize n to n. This is fine. Next we are going with a BIT array. BIT array, nothing but the binary index tree array. So I'll just go with self dot BIT. This is equals 0, similar one to the this one segment tree. So this one is nothing but sorry n plus 1. So this is fine. Now what are the methods basically we'll be going with? So see here what it does. Fenwick tree is a data structure that efficiently supports prefix sums and updates, right? So update method is required. Quite obviously update method is required. Usually whenever there is updation involved, then only we make use of the Fenwick tree. And one more thing I want to say, this one strictly I have stressed this one while solving the problems as well using the Java. So any problem that can be solved by a segment, this one Fenwick tree can be solved by segment tree, but every problem that can be solvable by segment tree uh, may not be solvable by this one Fenwick tree, right? It's not vice versa, but any problem that can be solved by Fenwick tree can be solved by segment tree, right? But it's not vice versa. Any problem that can be solved by segment tree may or may not be solved by Fenwick tree. Just remember this one, right? So this will be helpful. So this is fine. Now let's go with the this one update method. So I'll just go with def here. Let me go with update. So let me involve self idx this one, and let me go with the delta. This is fine. So within the update method, so I'll just go with a simple while loop here. So this one will be while index less than or equal to self dot n. So this is fine. So this will be self dot, we have considered bit, right? So this is fine, self dot bit. This one we have to consider index here, right? Index equals same thing plus delta. Plus delta we have considered, so I'll just go with the delta. This is fine. Now the final step is we have to move to the parent, right? So we will be going with a bitwise AND operator here again. So this is pure binary tree, man. Whenever you see plus index and minus index, right? Minus index means in the term we will be making use of the binary sorry, bitwise AND operator here, right? So this one, whenever we see like this, index equals index plus index bitwise AND operator here, this one will be minus index. So usually in the beginning, whenever I used to see this line, I used to come to know that this is solved using the Fenwick tree. I doesn't used to this one use the AI things, right? So whenever I used to solve the problems, or when I used to solve this one, see other solutions, whenever based on this one, I didn't know this one, the name of Fenwick tree at all, basically. So I used to see this line, oh, there is plus this one IDX and minus IDX, so this is nothing but the Fenwick tree. I used to think like that, basically, to be frank, right? So I just remembered that one. So this is fine. Now this is nothing but line number 14. We are just moving to the parent man. So we are done with the updation. We are done with the updation. So again, now as usual, we have to go with the query as well, right? So I'll just go with query. So in the segment tree, we went with this one, a build and the query. Now we are going with the update and query within the Fenwick tree, right? So this one will be self comma index, self comma index. This is fine. So within the query, first let me initialize result or s equals 0. This is nothing but the result man usually, right? So I'm considering the variable s, that's it. Or you can just call sum. So I'll just go with while index has to be greater than 0. This has to be true at any cost. So I'm just making use of the while loop here, right? So s will be s plus self dot, we have made use of the bit, this one will be index, right? So we are done with this part. So again, idx, this is equal to index minus, again the same thing, index bitwise AND operator here, we are going with, now this will be index, right? Simple, very simple, right? So we are just moving to the previous. Here we are moving to the parent, the line number 14. In the line number 20, we are moving to the previous, right? So finally we have to return what we need to return, previous. So I'll just go with the return s, right? So we are just moving to the previous, nothing but we are returning to I mean we have to return s here, the variable that I initialized to 0 initially, this one, right? So we are done with the Fenwick tree, this one class Fenwick tree. Basically we went with two methods, update and query, simple ones, right? So now let's do one thing, let's test, or let's go with the example usage man, simple one. I'll just go with a simple one, not to worry. So I'll just go with the ft for the Fenwick tree. This one class we have given Fenwick tree, right? Yep. So let me pass some number 5, right? So random number I have just consider 5, this one 5. So we have written update and query. First let's go with the update, then let's see the query. So I'll just go with ft dot, let me go with update. So let's add 2 at the index 1, right? So we have to add some number at the index 1. So we need to update, right? So let's add 2 at index 1. So let me add here 2 at index 1. So this one will be 1 comma 2. This is fine. So let me do the same thing for other index as well. So here let's add 4 at index 2. right? So random numbers. So this one will be 4, and let me add 5 at index 3. So this has to be within 5, as we have considered 5, Fenwick tree of 5 here, this one 5. Fine. So we have considered 1 at this one, sorry, 2 at index 1. So this one has to be, I have to give here 2 and 4. So this one has to be 2 and 5. Reverse. Let me reverse this one. Yeah, 2 and 5. Sorry. Sorry for this one. This is fine. Oh, this one has to be 3, third index, right? So we have added 5 at index 3. We have added 4 at index 2, and we have added 2 at index 1. That's what we have done, right? So now our updation is complete. Now let's do one thing. Let's query, right? Nothing but let's go with the prefix sum from 1 to 3. So I can just go in this way. Print of Fenwick tree. ft is the variable I have considered. So this one will be query of let me pass some number 3, right? So we are going with a prefix sum from 1 to 3. We are going from the this one prefix sum from 1 to 3. So what within the update, what is the numbers I have passed here? 2, 4 and 5, right? So I have to get the output. 5 plus 4 is 9, 9 plus 2 is 11. So the output that I need to get here is 11, right? So we are passing the number 3 here, which means are uh, we are trying to get the prefix sum from 1 to 3, from index 1 to index 3. In the index 1 we have the value 2, because we have updated with the value 2. From the in the index 2 we have the value 4, we have updated that one with the value 4. From the index in the index 3 we have the value 5, we have just updated this one with the value 5. So the total output we are trying to get here, this one prefix sum from 1 to 3, from 1 to 3, right? So here the output that we need to get here is 2 plus 4 plus 5, nothing but 2 plus 4 6, 6 plus 5 is 11, right? So let me give cls here. Let me try to run the code. So I'll just give here python. Let me right click, rename. Let me copy this one dot py, right? See here the output that we are getting here is 11, right? So the prefix sum from index 1 to 3 is 2 plus 4 plus 5, nothing but the 11. We are getting the desired output or the correct output. So whatever the code I have written works absolutely correct, right? So this is it for the Fenwick tree. Simple, right? So we went with step by step. I have explained you step by step, basically, right? Again, this part is very important. Again, I'm telling Fenwick is a data structure that efficiently supports prefix sum and updates on big of login. Just remember this. And it uses bitwise operations. See here, line number 20, line number 14, bitwise and operator, right? So it uses bitwise operations to store cumulative sums in a compact way. This sentence is very important. Again, each index stores the sum of specific range of elements, right? Each index stores the sum of specific range of elements. See here, right? 2 comma 4, 3 comma 5, 1 comma 2, 2 comma 4, 3 comma 5, right? So we are trying to get the prefix sum from 1 to 3. All we have to get the output is 11. So we have got the output 11, which is absolutely correct. So we are done with the Fenwick tree part. So let me summarize whatever we have learned so far. So Fenwick trees are memory efficient and faster to code than segment trees. Remember always this one, just remember, whenever there is updation required and whenever we want something in the logarithmic end time, right? So whenever intervals are involved and whenever the constraints are tight and whenever we want to solve the problem in logarithmic end time, then it is and whenever there is updation required, obviously, right? So it is better to go with a Fenwick tree. It is better to go with the Fenwick tree. Again, I'm stressing on it, whenever there is updation required along with the prefix sum, right? So it's better to go with a Fenwick tree. Why? Because Fenwick trees are memory efficient and faster to code than segment trees, right? It is faster to code than segment trees. So it is somewhat less complex, lesser this one, less complex than this one, right? Segment tree, right? Segment tree, uh, accordingly with the criteria and the conditions that they will be that they have given in certain questions, we have to change certain things and the code might be complex or lengthier as well, right? Compared to Fenwick tree. So this is better than it's better to go with the bit or the Fenwick tree, right? Again, Fenwick trees are memory efficient and faster to code than segment trees. They are perfect for prefix sum queries and dynamic updates. Again, they are perfect for prefix sum queries and dynamic updates, right? So we are done with the Fenwick tree part, right? So next we'll be discussing on the topic sparse table, the last one within this playlist. So sparse table will be the last one, right? So we are done with the Fenwick tree part. For now, this is it. Thanks for watching, guys.